There we go.
Okay, hi everyone. My name is Zhang, and I'm currently working in PNL. Today, my topic is the wildfire effects on weather hazards. So I want to acknowledge all the collaborators listed here, especially my mentor, Jiwen Fan. So as we know, the wildfires and the severe convective storms and they're associated with hazards like hail, heavy precipitation, and lightning and the flash flood really can cause significant property damage and the economic losses in the US. And in addition, the wildfires and the convective storms are also projected to increase in the future climate change. Then usually, the wildfires can impact the severe convective storms through two major pathways. One is to release the heat and impact the severe convective storm through the meteorology. And another is wildfire can release and also form aerosols to impact the convective storms through the aerosol radiation interaction and also aerosol cloud interactions. So there's few investigations link the wildfire and also these severe convective storms together with these two major pathways together. So this motivates our investigations. First thing is about, because as we know, like in the regional and also global climate models, really the heat flux of the wildfire is not considered. So the first step is we develop parameterizations of to account for the heat flux from wildfires in the Wolfram. So the major point here is that we add a temperature tendency, which is from the wildfire heat flux, to insert as an additional source term to the thermodynamic equation. And also we assume the temperature tendency is with an exponential decay from the surface to the injection height of the plume. The injection height of the plume is determined in a 1D plume rise model, which is described in Fretters in 2007 paper. This 1D plume rise model is incorporated in each grid column in the Wolfram grids. And once we determine this injection height, we also estimate the heat flux based on the different fire types. Basically, here we include the tropical forest and the extratropical forest, and also the wooded savanna and the grassland, these four types. And we got the burning area from the satellite observation. So combine these two information together, we estimate the heat flux. As we know that we already have the Wildfire as a detailed model to capture the fire spread and also fire plume dynamics, especially. But the disadvantage is that this is very computational costing. So that's why we want to develop a computationally efficient parameterizations in the regional scale Wolf simulation, Wolf model. So we evaluate this new model with new heat flux parameterization at a 3-kilometer resolution, which is usually applied in WolfCam. So we apply here is over the North Great Plain during 17 to 19 July in 2016, and we compare the three sites which sounding site is close to the fire points. And what we found is that after incorporating the heat flux parameterization, it just gives better simulation of the low level temperature for the places near those large fires. And further, we evaluate this new model at 1-kilometer resolution because when our focus is to simulate the severe convective storm. So we needed to evaluate that at this high resolution. And as a beginning, we select the PyroCV case, which is triggered by 2018 Wildfire in Texas, from May 9 to May 14 in 2018. For this case, we simulate one is with the wildfire using the WolfCam with our heat flux parameterization. We also simulate this case using the detailed Wolf S5 model. And to compare the wildfire impact, we also add a no wildfire simulate sensitivity test, which is remove the wildfire, both the heat and the aerosol emissions. So what we found is that actually here from the 2-meter temperature change due to wildfire before the convection, actually our model can produce the similar 2-meter temperature change due to wildfire as that from the Wolf S-fire. And we also get the similar plume height as well as the echo top height. We also compare, we found a sounding set at Kammer near the Malad fire. And what we found is that the fire and the wildfire using WolfCam is also similar with that from the Wolf S fire. And about the computational cost, the Wolf S fire just costs about 45% more. So which means our new model is more applicable to the weather forecast and also in regional and the global cloud resolving model. So when we look detailed into this case, we use our new model and we add a few more sensitivity tests. One is to remove the heat, only heat. One is to remove the aerosol from the wildfire. In this way, we can investigate both the heat and the aerosol effect from the wildfire to this PyroCV case. So firstly, from the perspective of the thermodynamics, here as we find that the wildfire contributes to the remarkable increase in temperature for this Malad fire region, which is marked as a yellow box here. It induced about 4 degrees above the ground, and also at surface it leads to the increase at about 5.5 degrees. And in the meantime, the relative humidity is decreased. But for the site A, which we see here, which is remotely from the wildfire, we cannot see any wildfire influence. And for the severe weather associated with PyroCV, we see here, which is mainly the heavy precipitation and also the hail and the lightning. We find that without wildfire, the heavy precipitation larger than 15 millimeter per hour, and also those extreme hailstone size larger than 20 millimeter in diameter, and also those very high reflectivity larger than 55 dBz do not occur, and the lightning stroke rates are also reduced by about 40%. Overall, we see that the effects of heat are much more important than those from the aerosol effects. But when we look in detail to the evolution of the convection, we find that the heat effect is playing a predominant role in triggering this strong storm, especially in this in the first few 2 hours. But after like 22 UTC, the storm is initiated and also developed to the mature stage. We find that aerosols is playing a significant role to enhance the storm intensity and also the hail and the lightning after that. So for this study, actually, we enable a model capability to account for the heat flux, and also in that way we can look into the heat and aerosol effect from the wildfire together and also respectively. But this case is a pyrocb case, which is occurred very close to the fire. So next, actually, we are thinking about for the fires, which is like a remote from the severe convective systems that we focused to see if there's any linkage between them. And also there's very few study. I think so far we didn't see much study about the wildfire, which is remotely from the convective storms. They have any linkage between each other. And because for example, because when we think that the Western wildfire, which is like usually happen in peak in the summer season, while the central U.S. convective system is usually happen in the spring system. So they are generally separated by seasons. But in recent years, as we found here, the wildfire intensity is increasing, and also the peak season is occurred much earlier. So that's why we're trying to link these two systems together to see if there's any possibility of the impacts of each other. And we further look at the concurrence of the Western wildfires and the central U.S. severe convective storms. We looked at into the year from 2009 to 2018, and the region we focus here is Washington State and Oregon and California as the Western wildfire region. And for the central U.S., we select here as the 10 states. And what we find is that the concurrent event with storms occurring on 3 or more consecutive days did not emerge until 2018, which means like not until recent years, like 2018, we cannot see these two events can be emerging at the same time. And also in another way, we found that there's a positive correlation between the number of daily hail reports with the burn area of the Western wildfires. So with all the listed above this motivate us to conduct detailed modeling study of this event in 2018. So for the severe convective events occurred in these 4 days during 26 to 29 July, which is occurred in central US, and it produced a lot of weather hazards associated with the flood and the hail, and also the damaged wind, which leading to over 100 million economic losses. And also in the meantime, we find that both the wildfire in the western US, and which is mainly in the California and Oregon, has been occurred at least 2 days before the storms. And also there's some wildfires in the local region, which is quite close to the region of the convective storm. So the major science questions for this study is that what are the joint and the respective effects of remote and local wildfires on central US severe weather? And also the second one is the effects mainly contributed by the released heat or aerosol, or both? Here is the model simulation and evaluation. So we used the model Wolfram coupled with spectrobeam with mosaic, and also accounted for the both heat and aerosol from wildfire using the heat flux as we described above. And we use a 3-kilometer outer domain to drive the 1 kilometer simulation domain, which is mainly covers the central US region of the severe convective storms. We also further conduct model sensitivity tests to investigate the effects of remote and the local wildfires, and also the respective role of wildfire heat and aerosol effects. So here, as we see we evaluate both aerosol, the AOD, as we see that the model can capture the transport of the wildfire from the western US to the region of the Wyoming and the Colorado. And also for the mean precipitation rate, the model can capture that, and as well as the maximum hail size. Then the major result is that we find enhanced occurrences of the heavy rain and the large hail. The joint effect of both the remote and the local fire increase the occurrences of heavy precipitation larger than 20 millimeters per hour by about 38%, and increase the significant severe hail larger than 2 inches in diameter by about 34%, which is pretty significant. And also the accumulated rainfall averaged over the central US over these 2 or 4 storms is increased by 5.9 millimeter, which is about 19%. Then we further look into the respective role from the remote and the local wildfire. So the number on the bars is the ratio of each effect to the total wildfire effect. As we see here, the remote wildfire effect contributes to the 67%, and also 60% of the increase in the heavy precipitation rates and the significant severe hail, respectively. For the accumulated rainfall, the remote wildfire also contributes about 66% of the total increase. So suggesting that the remote wildfire effect is more important than the local wildfire impact. Besides the respective role of the local and the remote wildfire, we also look into the heat and the aerosol effects. The values on the sky blue bar is the ratio of the total heat effect to the total wildfire effect. So which means, as here, the heat effects contributes to about 54% on heavy precipitation rate, and also 46% on the significant severe hail, suggesting that both the heat and aerosol effects from the wildfire are significant, because only the heat effect only contribute to about 50% of the contribution. And for the heat effect, we further look into the remote heat effect and the local heat effect. The values on the brown bar is the ratio of the remote heat effect to the local heat effect. So what we find is that of the heat effect, the 60% on the heavy precipitation and the 76% on the significant severe hail is from the remote wildfire. This further implies that why the remote wildfire impact is more significant than the local wildfire impact. Actually, the major mechanism behind here we find is that the wildfire in the western U.S. enhance the surface high pressure in the western U.S. and increase the westerly wind, which leads to a stronger moisture and aerosol transport to the central U.S. And the increase the aerosols over the central U.S. And in the meantime, we find that the central U.S. Has decreased surface pressure, and we also find the larger wind shear and also storm relative helicity in the central U.S. Combine these two together, that's why we see the hail and also the heavy precipitation of the severe convective system over the central U.S. is increased. About significance is that this study demonstrates a concept that the upstream wildfires can be an important factor influencing the severity of the convective storms. And also this impact may become increasingly important in a warm future, as both the western wildfires and the central severe storms are projected to occur more frequently, and also their occurrence period. The occurrence events are projected to be more frequent and also more common in the future, because the fire peak season is occurred much earlier. And actually, I think thanks for all your attention. I'm ready to take further questions. And I listed the two papers associated with my talk here, and you can find more details from these two papers.